Welcome back, ladies and gentlemen. And now it's time to welcome Dr. Brett Lane, the Chief Technology Officer at Panduit, who'll be sharing his thoughts on innovation for a decade of interconnection. Brett has 25 years of experience in research, development, and management of network and electrical infrastructure solutions. He is the Chief Technology Officer of Panduit Corporation, headquartered in Chicago, US, where he's responsible for driving sustainable business growth by delivering a continuous flow of innovative solutions through research, advanced development, and corporate entrepreneurship. We welcome Dr. Brett Lane, and the stage is yours, Brett.
Great, thank you very much, Steve, and good afternoon. I'm really excited to be here and give this talk. It's a little bit different talk. I do a lot of talks and I travel the globe as I talk with our customers and partners. And oftentimes my talk focuses on products, but this time Steve and Basil and Rula challenged me to talk about the future, distant future, and how our technologies can drive business value for our customers. Before I get started, I do want to apologize. I know the promo had Elon Musk and Jeff Bezos, Jack Ma, and Satya Nadella, the CEO of Microsoft, and unfortunately they couldn't be here with you this afternoon, and so they've asked me to say a couple words. So I hope you enjoyed the talk. Really what I want to talk about is interconnections and how they've shaped the last several decades, and maybe give you some perspective on how we as partners are going to shape the decade of interconnections in the future. But before I get started, I wanted to take a look back at where we've come. And accessing the internet is one of the most common experiences we all share today. Its origin dates from the 1960s in ARPANET, where the internet was primarily used for military purposes. The invention of the first browser in the early 90s provided the first public access to the internet. And I still remember that first time I accessed it in the University of Texas in 1995, and it was amazing. I could browse from page to page, and I'll always remember that day. Interestingly, many decades before the invention of the internet, a visionary storyteller from Argentina, Jorge Borges, wrote a story titled The Library of Babel, which is shown here. The library contained an infinite number of hexagonal rooms filled with 410-page books that contained every possible combination of a 25-character set. So therefore, it contained all books of the past and all books of the future, a seemingly endless labyrinth of information. Now, this story has been considered by many experts as the inspiration for the first web browser, which allowed users to access a seemingly endless library of information by moving from room to room, or for the internet, page to page. Zooming forward a couple decades, this map shows internet usage in 2000. After the first browser was invented in the mid-90s, and by the late 90s, there were very few computers connected. Only about 1% of the world's population was connected. However, by 2000, the internet was growing rapidly. And by 2000, about 7% of the globe's population was connected. In the 90s, the concept of cloud computing was invented by Salesforce, no less, which allowed users and customers to download applications from the web. In 2010, about 30% of the world's population was connected to the internet. From the map, you can see that most of North America and Europe were connected, and the total usage was about 2 billion users. In this decade, many of the applications we use today were released: Chrome, YouTube, Skype, Facebook, Twitter, Netflix, streaming. Also, the iPhone was released in 2007, which became a major driving force for internet growth. Cloud deployments, many of which started in this decade. Amazon Web Service started in 2006. Alibaba Cloud started in 2009. Began to gain momentum, and businesses started to migrate some of their critical workloads to the cloud. In 2017, the latest map that I have, 45% of the world's population was connected to the internet. Today, this figure's about 60%, or about 4.5 billion users. During the last decade, even more cloud service providers were launched. Microsoft Azure started in 2010. IBM Smart Cloud, Apple iCloud started in 2011, and Oracle launched their cloud product in 2012. Also, over the last decade, financial applications operating in the internet have exploded. Alipay, WeChat, both have more than 1 billion daily active users based upon the explosive growth of the internet in Asia. To compete against PayPal, similar applications like Google Wallet, Apple Pay, and Samsung Pay were launched. Considering the importance of the internet today, it's sometimes difficult to believe how recently the applications that we use each and every day, when they were released, and especially the younger generation. I've got 5 kids, and they're awesome detectors at telling me when the Wi-Fi is down. How did we ever live without these applications? And the exciting part for us as partners is that they all run on the infrastructure that we design, build, and install for our customers. So over the past 30 years, there's been an explosion of interconnections, and it's only going to accelerate. Earlier this year, we were scanning the periphery about what new technologies we could deploy together. We were excited about many items, the cloud and the edge. We just learned about how the cloud has proliferated over the past many years, and that's only going to get faster and more important to our business customers. Data centers are going to be deployed in the edge as latency becomes important. Artificial intelligence and machine learning can make great use and quickly go through volumes of data, bringing business value. Wi-Fi and 5G and the wireless technologies. As users demand more flexibility, these access technologies are becoming more important. Wi-Fi 6 is just beginning to roll out, but we're already working on Wi-Fi 7 technologies and 5G being massively deployed globally. And the digital enterprise, the smart building, our customers are demanding a more efficient and more tailored experience as they interoperate with their workplace. Finally, we've all heard about IoT and the proliferation of devices, 50 billion devices. And how can we bring value to our customers to make use of that data with artificial intelligence and machine learning? And finally, the convergence of information technology and operations technology to make smart factories. So we were working on all of these technologies, working on solutions that we could bring to you, our partners, and finally, our customers. But then the coronavirus hit. On January 9th, 2020, the World Health Organization reported a novel coronavirus in Wuhan, China. This was also the first reported death. On January 28th, globally, 100 deaths were reported. On February 10th, 1,000 deaths. On March 11th, World Health Organization declared a global pandemic. In early March, the United States began to shut down, and my last day in the office was March 13th. March 20th, 10,000 deaths. April 2nd, globally, 1 million cases. April 9th, globally, 100,000 deaths. Just a month later, on June 9th, globally, 500,000 deaths. On June 28th, more than 10 million cases globally had been reported. In July, vaccine makers Moderna, AstraZeneca, Pfizer, and BioNTech all announced promising results from phase 1 and phase 2 vaccine testing and rapid their pace to phase 3 trials. On August 10th, globally 20 million cases. On September 28th, globally 1 million deaths. November 8th, 50 million cases. And just last week, December 3rd, the UK approved emergency use of Pfizer's and BioNTech's vaccine and began usage immediately. So what was the economic cost of this horrific pandemic that we've all faced in 2020? Well, according to the IMF, in 2019, the global economy or economic GDP stood at $88 trillion. This map shows the declines or the change from the year prior, and it's forecasted to be minus 4.4%, or about $4 trillion in 2020. But you can't just consider this 1 year change. You have to consider how long it takes to get back to the value we would have been, which is about 8 years. The coronavirus pandemic will provide impact over 8 years. And the total estimated value is about $30 trillion, which is 4 times the cost of the last Great Recession in 2008 and 2009. But it's hard for me to grapple and feel and own these large numbers. What we feel are changes to our lives. And I thought these pictures resonated far more strongly than $30 trillion. It's the work from home. The globe has migrated from working in office and commercial buildings to working from home. I have 5 kids, and sometimes my environment looks like the picture shown here. I was due to travel to Italy in February and have research and development discussions with one of our partners, Prismium Group, at an R&D summit, and that trip was canceled. And so we're not traveling anymore. There's been essentially no travel for the past 10 months. Again, I've got 5 kids, and they've migrated to e-learning. Sometimes that's no learning because they're accessing YouTube and TikTok and distracted. And so it's really been very difficult for them. I'm a big sports fan, and sports stood still for about 3 months, essentially no sport whatsoever. And now what sports have returned, they've returned with little to no fans. It's disappointing. Sometimes when I see clips of events and matches from years past, I see all the fans, and it's sort of shocking at this point. Restaurants, it's very difficult to go out. We play the coronavirus very conservatively, and so we don't go out very much. And many of the establishments that we enjoyed going to in the past are no longer there. So this pandemic has been very difficult for the small business. And so these are the items that have all touched our lives, and we all wrestle with and think about as we reflect on 2020. So clearly the globe.
Sorry, Brett, just sorry to interrupt. There's a lot of background noise of like paper rattling or something, or maybe it's your microphone, I'm not sure. Just there seems to be some.
Okay, thanks, Steve.
Okay, no problem. Sorry to interrupt you. Carry on.
No problem. So clearly the globe is in a generational crisis, and the medical industry came together to find both a treatment and a vaccine. The average vaccine took 10 years to develop, with the fastest being the mumps in 1967, which was 4 years. Considering the work began in earnest in early January and was approved for emergency use early last month, it took just a little over 10 months to develop the coronavirus vaccine. This effort involved thousands of researchers at hundreds of laboratories around the world spending billions of dollars. This interconnected development effort shattered the record for a vaccine development. So the question is how? And that's what I wanted to spend a little more time on. But before I get started, I'll admit I'm not a molecular biologist, and I have a limited understanding of the medical elements of the biology and chemistry involved. Instead, I wanted to highlight the importance of computer simulations and artificial intelligence in this journey. But we do need to understand the basic methods of how the virus spreads. So shown in this picture on the right, if you look at the upper part of the figure, is the coronavirus. And it's got a prevalent feature called the spike protein, which is shown in purple and gray and green. And shown on the bottom is the host cell. And how the coronavirus works is the spike protein interacts with the ACE2 receptor to inject its blueprints and hijacking mechanism from the spike protein through that ACE2 receptor. And so that's been the focus of research over the past 10 months to understand the mechanism by which these interact. And so the effort very early on was to simulate the interaction between the coronavirus and the host cell to augment the experimental and clinical work. What I'm talking about is simulating these millions of atoms of the coronavirus, particularly that green part, and that's called the receptor binding domain, and the host cell and its AC2 receptor, and how they interact on the femtosecond time scale, or 10 to the minus 15 seconds. If we zoom in even more to look at the coronavirus receptor binding domain, we can begin to see why the vaccine development typically takes so long. What's being shown in this animation are the various molecules and their interaction with spike protein's receptor binding domain. Each molecule is rotated and translated and reconfigured against the countless configurations of the protein chain to evaluate the atomic level binding between the molecule and the protein. In layman's term, essentially the goal is to throw a wrench into the operation of the RBD, thus prohibiting it from attaching to the cell and replicating itself. To identify the most promising molecule compounds amongst the billions of small molecule compounds in combination with the millions of poses with a virus protein, supercomputers were called into action. On March 23rd, the COVID-19 High Performance Computing Consortium was announced, which provided the world's researchers with access to 16 pools of supercomputers from academia, national laboratories, industrial partners like IBM, AWS, Google, and Microsoft. In total, this was the largest interconnection of compute resources in the history of mankind. And it tackled not only the simulation above, but also many more as research sought to rapidly appreciate therapeutics and vaccines. Now, hopefully this is looking a little more familiar. Shown here is the Summit supercomputer located outside Knoxville, Tennessee. Until this past June, Summit was the highest performance supercomputer in the world and cost over $200 million to build. If you're curious, yes, there is a ranking system for supercomputers, and it comes out twice annually in June and November. And they rank supercomputers on the basis of their ability to compute floating point operations per second. Summit is able to perform about 200 quadrillion or 1,000 trillion floating point operations per second. It also has about 250 petabytes of storage capacity. And running Summit isn't cheap. It requires about 10 megawatts of power to cool the thousands of nodes and requires about 15,000 liters of water each and every minute to keep the tens of thousands CPUs and GPUs cool. The size of Summit is about 520 square meters, or about the size of 2 tennis courts. And it houses 4,608 nodes or servers and about 260 racks. These are pictures of the back of Summit that I suspect are looking not so different than a bigger data center installation that you might have been a part of. On the left, you can see the back of one of the cabinets. You can see the servers. Those are the 2 RU servers. Each of the 2 RU servers has 2 IBM Power 9 processors with 22 cores each and 6 NVIDIA Volta GPUs. There are 18 servers per rack, each connected with 36 port top of rack switches with 100 gigabits per second InfiniBand direct attach copper cables. Those are the cables on the right side shown in black. These 2 top of rack switches were connected to each of the 18 648 port director port switches via 100 gigabits per second InfiniBand fiber cables, and those are the cables shown on the left in aqua. On the right, you can see some of the 300 kilometers of high-speed multi-mode fiber cabling being installed into Summit's Fiber Runner Raceway. Now, between the top of rack and director switches that are connected with fiber, each of the 100 gigabits per second signals actually is carried by 4 independent 25 gigabits per second signals. So each cable has 4 fibers, 4 transmit and 4 receive, each operating at 850 nanometers at 25 gigabits per second. Shown here is what we call an eye diagram, which is the superposition of a large data stream of ones and zeros, just like might be seen if you were to look at a stream of data of information on one of the optical fibers between a, say, top of rack switch and a director switch. Obviously, this is a 2-level communication scheme, just ones and zeros. And you can see the rising transitions from 0 to 1 and the falling transitions from 1 to 0. You can also see a little overshoot as it rises and a little undershoot as it falls. But overall, this eye diagram is very open and easy to distinguish between the ones and the zeros. The time duration for one data symbol used in the Summit supercomputer is just 40 picoseconds, or 40 times 10 to the minus 12 seconds. This would be the time between where the eye crosses in the middle of the figure. Over the past 40 years, almost all communication with data centers has used this basic communication technology. However, we recently reached the end of just being able to modulate the lasers and detectors more quickly. Doing so has become more difficult, and so we needed another way to pass information more quickly for the needs of supercomputers and other high bitrate communications. And actually, Panduit has been a leader in this space in recognizing the need to develop technologies to improve the speed of interconnection. Shown here is another eye diagram. However, you see it looks markedly different. You see that there's 4 levels of information, 0, 1, 2, and 3. And you'll see the associated transitions between those levels, 1 to 2, 1 to 3, and 1 to 4, and vice versa. About 10 years ago, we recognized the need to increase the amount of information we could transmit per unit time by moving from a 2-level system to a 4-level system. We collaborated first on the theoretical modeling by partnering with the leading researcher at Stanford, Professor Joseph Kahn. I also hired one of the brightest researchers I've ever met, Dr. Jose Castro, who had done a PhD at the University of Arizona, which is one of the leading institutions of higher modulation schemes in optical communications. Over the following 8 years, we led the industry to bring this modulation scheme into the optics domain. No, we certainly didn't do it alone. However, Panduit researchers led the theory, the modeling, and the experimental validation of how PAM4 is a viable technology that can improve the state of interconnections in the data center. And we didn't just focus on the electrical part of the equation, we focused on the optical part as well, as we were pioneers in the advancement of the next generation multimode fiber, OM5. And so if we return to the next supercomputer, it's already under construction at the same facility in Tennessee. It's called Frontier, and it won't use 100 gigabits per second. Instead, it will use this modulation scheme to achieve interconnect speeds of 200 gigabits per second on each and every one of its thousands of links. Here's a picture of our innovation center. It demonstrates our commitment to R&D. Innovation is in our DNA. It was given to us by our founder, who was passionate about innovation. I'm hopeful that each one of you can visit this facility, because it really speaks volumes when you can see it and you can touch it and you can talk with some of the researchers. It's awesome, and almost every customer that we bring becomes a Panduit customer and partner for life. There are 200 innovators from each of our businesses. It co-locates simulation, design, prototype testing and manufacturing. There's 18 laboratories. There's fiber, copper, electrical, wireless, AV, thermal, industrial, et cetera, et cetera. And we even have our own very own small supercomputer. No, it's not a 200 petaflop device. It's merely tens of teraflops. But we use it in our own simulations, and we've used our own machine learning algorithms to improve some of our products. So for example, the OptiCam 2 termination tool. We have the best equipment and the best engineers. We've also got an advanced tooling facility so we can bring designs to life in a matter of days instead of months and weeks that our competitors use. We take an outside-in approach by looking at the ecosystem, and we use commercial partners across our development scheme. And this includes taking leadership roles in standards bodies, just like I spoke about over the last decade or so when it comes to optical fiber communication. Within R&D, we have 7 distinctive competencies. These are areas of expertise that were better than the competition: mechanical, RF and electrical, optical, software, network architecture, industrial automation, and thermal. We leverage and interconnect these to create innovative products. However, it's not enough to only work internally. As you saw with the development of the coronavirus vaccine, experts across the world must connect with each other to share, learn, innovate, and solve. That's why we invest so heavily in our alliances and our partner network. Our vision of higher speed interconnect started more than a decade ago. Shown here are some of the technical partners with whom we worked on next generation modulation and fiber transmission technology. From academic institutions across the world like Stanford and Creel and Chalmers, to leading industrial firms like Cisco, Avago, FIT, Mellanox, and Broadcom, to name a few, to standards bodies like IEEE, TIA, Fiber Channel, and our partners like Prismium Group, and even our competition. We connected and led the world's experts to bring future technology to the present. And we continue peering into the future for the next breakthrough technology. Again, the same is needed to increase the speed of interconnect. And shown here is a hollow core fiber. In a traditional fiber, the index of refraction is about 1.46, and so light propagates at about 70% of the speed of light in a vacuum. However, in a hollow core fiber, similar to what is shown here, it can be designed so that its effective index of refraction is very close to 1, bringing its propagation velocity to 99% of the speed of light in a vacuum. Therefore, the speed of interconnects can be improved by about 30%. This one day will bring a big improvement to those applications where latency is the most critical, for example, high performance computing. This is just one example of the technologies that we're working on, and you'll see in many, many years to come. So as we're on the cusp of turning the page on 2020, thankfully, in fact, and looking forward to 2021, I'm excited about the future. I'm excited about the opportunities in data centers and smart buildings, in 5G networks and in Wi-Fi networks inside buildings. And I'm excited about the value we can bring our customers with IT and OT convergent solutions. The amount of interconnections is going to continue to grow rapidly, and our customers need us to bring reliable and efficient networks to their networks. On occasion, that will ask us to solve the most difficult and perplexing challenges that our competition can't address. And it won't only be technical. They'll ask us to meet impossible deadlines and logistical challenges. And I'm looking forward to working with you to meeting these challenges. Thank you and good afternoon.
Thanks, Brett. Thank you very much for sharing your expertise. We have time for probably just 2 questions if we can. The first one, you showed the hollow core fiber. When do you think that will be commercially available?
Oh, thanks, Steve. Great question. In fact, that one is just on the, has just been demonstrated kind of in an academic and a very sophisticated research domains. And so the cost is very, very high for that fiber. For example, thousands of dollars per meter. And so to become commercially viable, I forecast it's going to be about 5 years at least to see any significant commercial adoption.
Okay, great, thank you. And I have another question as well. I heard a lot about data centers moving away from obviously multi-mode fiber in favor of single mode. And I saw the multi-mode fiber was installed in the supercomputer you showed. What are your thoughts about the longevity of multi-mode fiber in the data center?
Oh, thanks again for the question. It's a great question. Yeah, a lot of naysayers have been saying that multi-mode fiber is dead, just like people have been saying copper is dead. But as you saw in the picture, both multi-mode fiber and copper are commonly used, and I see both of those media types in wide-scale use for many generations to come. I did refer to 200 gigabits per second over multi-mode fibers. There has been standards up to 400 gigabits per second already approved. And so, and as leaders in the standards bodies, we know that it'll be contemplated for beyond 400 gigabits per second. So 800 gigabits per second and maybe even 1.6 terabits per second. And so I still believe multi-mode fiber has a role to play within our customers and our partners' data centers. And I look, and I believe it'll be in use for at least a decade into the future. So it's still going strong in my opinion.
Fantastic. Well, Brett, thank you very much for your time, and thank you again. And for everyone that's listening, we now come to another short break, basically 8 minutes of break, and we'll be back on the hour to listen to our last and final speaker, Jamie Swigert. Thank you, everyone. See you in a few minutes. Thank you.
Thank you.